Perfect. Right, hi guys, about ready to start? I'm Ali Brown, Director of Graphics Engineering at Cloud Imperium Games. I'm from the UK studio, which is called Foundry 42, and I'm here to talk about the visual effects in Star Citizen. Specifically, it's going to be mostly about our damage tech used for our ships, but a few other bits and bobs. Hopefully, it's quite specific to our game, but hopefully some of it will be useful for you guys in general. So, Star Citizen, I'm not sure if many of you have heard of it or not, but the company for Cloud Imperium Games is founded by Chris Roberts, who's a guy that made some 90s classics games like Wing Commander and Privateer. And Star Citizen follows in a similar vein to that. It's a space sim set in the future, quite an ambitious game design, but quite far beyond what these 90s classics like Wing Commander did. It's that, but extremely open universe. So the interesting thing about it is that it's from a first-person perspective, so rather than just being locked into your cockpit of this, you're free to explore, walk around space stations, planets, look at your ship, walk through the entirety of your ship. That's interesting and quite a challenge for us. It makes the scale and the scope of the game pretty massive. So as a graphics programmer, that presents quite a few challenges to us. So the gameplay, I'll just give a brief idea of it. We have a combat, exploration, trading, and mining, like it says, but there's a whole load of other gameplay things we've got in there. Predominantly, it's going to be like an instanced MMO, so we'll have multiple servers. It won't just be one world, but each server will handle one part of the universe, say like one star system or one planet or something like that. But as well as the MMO, we've got a full single-player campaign called Squadron 42. Now, if anyone has heard of Star Citizen, they've probably heard the next bit, the fact that it's a 100% crowdfunded project. It's been pretty successful. In fact, actually, it's the most successful crowdfunded project in the world by quite a stretch, I think like 4 or 5 times bigger than the next one. Along with that, we have like 700,000 backers or something like this. We have quite a lot of focus on us from the community, so they appreciate seeing things like this to know what we're doing and what we're up to. So at the moment, the game is in an open alpha state. We split the game up into different modules. We're developing them all in parallel, and then we're integrating them into the public build one by one. At the moment, we've got a few of them out, but it's probably, say 30% of the game is actually, or 20% of the game is actually available for the public. So yeah, because we're crowdfunded, we couldn't really start from scratch. So we didn't really have the time, so we started with CryEngine, obviously Crytek's engine, very mature engine, because all the standard rendering effects you'd expect for a modern engine these days, the physically based rendering, all the third and forward plus, lots of different anti-aliasing modes, like it says. They also, Crytek could give us quite a lot of great support as well, get an engine up and running and get the game working, so that's been really useful. So I'll just briefly show some images of the game. I've got a video at the end we can play if people want to see it of the actual game, but I'll just try and get to the graphicsy bits. So these are just some of our environments that are released to the public already. A few in space, one on the planet side. And let's play a really brief video, which might require some explanation. So the ships are a really big part of our game, being a space game. So, is this playing? Yeah, so the ships are a big part of our game, so we put a lot of emphasis on making sure they look good, and we produce these like mini adverts for the game. They're all based in the fiction, so they're all from like an advert from RoboCop or Starship Troopers, where like it's all as if it's in the universe. So that's display. This is all taken from in-game footage. Okay, so yeah, that was a brief clip shows. We're going through pretty high-end visuals. A current high-spec PC we're considering will be more like a mid-spec PC by the time we release the first version of the full game, which is probably about the end of this year we're aiming for. Currently, it's a DX11 only game. We don't support any older hardware, but obviously we'll be looking towards the new APIs in the coming year. So yeah, this is the ship we just saw a minute ago. It's made by one of our really talented eyes called Neil McKnight. If I just zoom into it and have a look inside. So this might not seem relevant at first, but I'll just talk you through some of this. The cockpit in these ships, or in fact the entire ships, are a billion times more complicated than you might expect for a game. So all this obviously is quite high res, a lot of polys in here, but everything in this ship moves and animates and actually is part of the game. So everything from obviously the joysticks to the throttle, the character will use these, all the buttons. Then user interface, little HUD screens there, or actually they are the actual HUD for the game. The pedals, the ejector seat, absolutely everything in the cockpit has a function. The reason I mention this is because that obviously has quite a significant amount of data that comes with it, a lot of draw calls, and it's a bit of a nightmare for us graphics programmers to try and have to make all this run at a sensible frame rate. So, yeah, as I just said, we have quite a lot of polys. I tended to find in the last gen games I worked on, we had like an 80-20 split between type of geometry and textures. It's more like 60-40 now, ending up with a lot of geometry. And that forces us to have to use quite a lot of streaming. So the streaming system is constantly working really hard in our game. And we tend to have a lot more assets than will fit into GPU memory. We've easily, in a level, we might be dealing with 8 or 9 gigs worth of data. So trying to keep the right resources resident is tricky. Obviously, that's where DX12 might, in the future, help us a little bit, have a little more explicit control of that, but for now, it's a tricky situation. So just talk about how we have to manage this situation. So initially, we just allocated more resources than we really had space for. That works to an extent. Obviously, you do put on a lot of emphasis on the driver there. And eventually, if you do that, then you're eventually going to get some paging, some GPU stalls when it doesn't really know what you're going to do. And we have situations where we'll say we only need a small percentage of our resources actually to be used each frame. So things like LODs, we don't need all LODs in a single frame. We'll only need one of them, but it's hard to manage that with the driver. But where we really fall down is we have these damage states, which is where we'll model a ship, say 5 times over for different levels of damage in the game, and then when it gets shot, we can swap for one of the alternate assets. Now, they're already loaded in RAM, but swapping them out in the GPU obviously comes with a significant hit, especially with the poly counts we're dealing with. And because they're mutually exclusive, it's difficult to manage that. If they were all on the GPU, then we would have very little memory actually available to us to play with for polys. But if they're not on the GPU, then we have these paging issues. So, yeah, mentioned some of this. So we did find that using tools like GPU View helps a lot in tracking these things down, as does speaking to the GPU hardware vendors. And I mentioned before, DX12 would help a lot in these cases to either diagnose or be a lot more explicit on how we manage these resources. But ideally, we just want to get rid of this situation. It's just not an ideal use of the memory. So we went to try and identify all the areas of the game where we have these type of mutually exclusive assets and try to just remove them. So for LODs, it's easy for us to predict which LOD we need. So that's quite straightforward. But these damage states are the real problem that were hurting us badly. So some of our ships, even that small ship we just saw there, might cost about 15 or 20 megs worth of geometry. But the actual, in the original, the pristine version we call it, but the damage states bring that up to about 100 megs. And now if you times that out by the number of ships we expect to be flying around, you easily exceed the GPU budgets of the hardware, the memory budgets of one of the graphics cards today. So yeah, we just set on a mission to try and avoid all these mutually exclusive assets. Here's just a picture of one of our ships cut up into the various pieces with just some of the damage states. Each ship is about 10 pieces, 10 to 20 pieces. So I've mentioned before, we have about 5 different damage states for our ships, and we'll switch them independently when you get shot. And all of these need LODs, so you multiply that out, and you end up with about 200 meshes for one ship, which is obviously a bit of a nightmare for the artist and the engine to actually handle. So we went about trying to improve the situation. So the key goal was to be less art intensive, and also less memory usage in total. We wanted to make better use of the hardware, and also while we're at it, we thought we might try and push the visuals a little bit further. So this is the type of things we were hoping to go after. These some pictures of some real damage to planes. So starting from the left, you've also got things like showing the paintwork there, rusted. You've got holes in the hull. You've got like an interesting shape cut out in that middle one. On the right-hand side, you've got the paintwork being burnt and then exposing the metal underneath. So our key idea of where we're going with this damage system was to drop all these damage states we had, the 25, 50, and 75% damage states. And instead, we just wanted to store the damage we've inflicted on the ship in some type of more GPU-friendly way, and then to use that in the pixel shader to then apply some type of visual representation of the damage. Now, we knew we were going to use direct compute to try and help us with this, and other DX11 features. And yeah, we just kept the 100% damage states just for when say you destroy a ship and it's an missile explosion. We did need a significant silhouette change at that point, and shader changes couldn't really pull that off. So here's an overview of our pipeline. So on the left, we start with our mesh data and the impact data, which might be things like the location of a hit, the size and strength, and whether it was an explosion, a physical bullet, or what type of bullet it was. The top side is type of our standard graphics pipeline, but we also have these two textures, two maps, position map and a damage map. And we use compute shaders to fill damage map with data from the impact, and we have a compute shader that also runs every frame to type of update this damage and do any simulations we want to run on that. And then we feed this into the standard rasterization pipeline to then actually do the shading of the ships. So this is just implementation details specific to our thing, but we chose to model rather than just damage, like 0 to 100, we decided to split it up into 4 different categories so we could get more physical type of physical simulation going. So we have deformation, thickness, temperature, and burn, the 4 quantities we decided to model. I'm showing a little quick diagram here, so we assume we have like paint sitting on top of metalwork, and then we can burn that away, and then we'll expose the metalwork, and then cut holes into it, and then bend the whole thing inwards as well. So yeah, so to store this damage data, we decided, as it was mostly just surface damage we needed, and we needed a consistent resolution for this. Standard 2D textures fit us quite well. We did look at using something like 3D textures, arctrees, or using the vertex data, but they either came with too much of an overhead or made the algorithms too complicated to optimize easily. So we also needed a geometric representation of the ship on the GPU. And we, again, opted for quite a simple solution, just storing an object space texture of the ship so that we now can render the ship into object space and store the position for every pixel, and then we have like a nice, easy format we can deal with on the GPU. However, our ships are animated, so that wasn't quite as simple as before. We have like wings that fold back and flaps and cockpits open, close, hangar doors, all these types of things. So we use the alpha channel just to store the index of the bone so that then we give you an example here. So on the left, we have our position map, so that's an object space map. Behind it is the alpha channel, which is like the bone index. So by reading them two, we can then skin the ship and then work out where in world space a fragment is. On the right-hand side is an example of one of our damage maps, which is just showing a ship after it's been hit by a few explosions and a few bullets. The smaller spots are bullets and the larger bits are explosions. So adding damage into this is where things start getting interesting. So as the UV layout of them textures is like completely artist defined, it's fairly arbitrary, which means that if you want to find a specific part of that texture that might be next to a certain impact, then you have to effectively read the entire position map, skin every single position on it, work out the world space position, and then only then can you then start doing your calculations to say how close is this particular pixel to this or this texel to my explosion. So we wasted like a tremendous amount of GPU doing that. The algorithm's not very efficient. We spend most of our work reading that texture and doing the skinning, so it's quite bandwidth limited. So we needed to find a solution to this. So we also have potentially we'll have multiple ships, and each one of them will be getting shot multiple times per frame. So yeah, that overhead adds up to be quite significant. For a single ship, a small ship like the one we saw before, it's not too bad. It's fractions of a millisecond, but when we extrapolate to the game design we have, that would have added up to a significant part of our frame. So yeah, we just needed to find a way to map the GPU to these specific areas much quicker. The textures, obviously, it's mostly spatially coherent. So your standard type of approach here would be to split the texture up into smaller chunks or tiles and then just have a calculate some bounds of that and do some type of early out, a bit like a high Z buffer. But this type of approach isn't quite as easy as it might seem because of the fact we have our ships skinned, so you can't really calculate a fixed bounding box or bounding sphere over any particular part of the texture unless you account for what the skinning is going to be doing. So also the other problem was, even if we could do that, it's hard to avoid wasted work in a pixel shader. There's no communication between the various threads, so there's very little you can do to try and bail out other than the type of the stencil buffer approaches and things like that. So instead, we opted just to use a compute shader here, using two main design ideas of using the thread group shared memory and also dispatch interact. Our key idea was to type of calculate, rather than just one bounding sphere per tile, which, like I said, we couldn't really do because we have the skinning idea. We calculate n bounding spheres per tile to handle the fact that each small tile of our texture might have several different bones within it. In practice, that's the limit we've set at about 4. It obviously depends on how the artist has unwrapped the model, but in practice that works fine. And what we can then do in the compute shader is we can spread this cost of testing these bounding spheres against the impact location across multiple threads. Now, that lets us bail out of the compute shader much quicker if we don't need to do any actual work for the areas of the texture that are far away from where the impact actually occurred. But it doesn't actually give us much of a benefit in speed because we have, say 64 threads in our thread group, say like an 8x8 bunch of texels, and we only have 4 or so bounding spheres typically, so we still have 60 threads that are just sat there idle. But actually, it doesn't turn out so bad when you consider that our impacts aren't just like when we hit a ship, we don't fire one frame splat. We actually, the impacts take many frames to occur, and some of them, things like when you have a laser shooting your ship, it leaves like a glowing type of ember there, so that dies down over several frames. So the end result is we end up with many impacts in one particular frame, and we end up with, I don't know, 10, 20 impacts easily happening at once for a larger ship. So our idea here was to then, so if we have, say, a thread group size, say 64, instead we just decided what the maximum number of hits we might expect to deal with, say 16, and the maximum number of bones we expect to deal with is 4. And then we can amortize the cost of testing all of these bounding spheres against all of these impacts for all the different bones all in parallel at the same time. And then we just, if any of them pass, if we find an intersection with a bone in a specific tile, then we just increment a counter, and then we can actually go on to do the real work, the guts of the work. So, let's go back on. So that saved us quite a lot. That is a significant improvement in performance, and it was a big benefit for us. But we wanted to try some different techniques as well. So we were looking into an alternate technique, which we are still investigating, but it hasn't turned out to be as much of a winner as we'd hope. But the alternate is to do pretty much the same thing, but then to store the results of these intersection tests between all the bones and the impacts, and then store that into another buffer, and then to call a dispatch indirect and do a second pass over this data. Without going too much detail, it's theoretically more efficient. It saves redundant work, but the overheads of having to save out the separate buffer and then call dispatch indirect and then read that buffer again, it ends up quite a significant overhead. So it's not a clear-cut case, but because our game's still in development, we've got that type of in the bank in case we need that approach. We might find that for a particularly large ship that's been shot a particularly large number of times in one frame, it might make sense, but in general, the simpler approach actually worked better for us. And just before I show some images of what this tech actually achieved, let's go some extra little details. So we use parallax occlusion mapping. It's obviously been used for many years now, but it always seems to fall down on like the silhouette edges and issues like this. In our particular case, we use it for the guts of the ship, inside the ship, which conveniently we never see the silhouette of them. So it's a perfect use of POM there. And it allows us to keep the internal bits of the ship that we model to much lower poly, and also saves a lot of artist time, so they don't have to model so much of the guts of the ship when we start blowing it up and cutting it into pieces. Recently, just in the last week actually, we added screen space height map. So this is using, there's a blog post from Mikkelsen, it's really great, and there's a few papers on it. So we have, as part of this damage map, we store how much we've dented and cut through the surface, which we interpret as a height map. but we don't have the tangent information, and we don't really want to store it. We don't have the memory for it, and the performance as well, the vertex throughput. So instead, we use this idea of doing a screen space height map where we calculate the gradient in a screen space and use that to perturb the normal. We use DDX and DDY for that. It looks pretty good, but as Mikkelsen pointed out in his work, when you get really close, it looks pretty bad because of bilinear filtering, because it's only linear. When you zoom in too far and you start magnifying the texture, the gradients are always linear, which effectively, the end result is you end up with DDX, DDY, returning a constant answer, and therefore you get like a pixelated look. He suggests one approach to solve that, which is storing more data, but we're quite memory sensitive, so we calculate an approximate gradient and then take 2 extra samples a pixel apart to try and get a better approximation of the gradient using forward differencing. So we pay a little bit more performance cost, but it saves us the memory hit. And we only need to pay that when we're under magnification, so we branch out and avoid doing that work when we're further away. It ends up being really convincing, actually. It's really useful. A few other small things. So as we mentioned, we do some type of heat dissipation simulation. So when we fire and we burn the hole, we can make that heat die down over time. And we can cut holes out using clip HLSL function. This required a little bit of care, and it's going to require a bit more thought from us because putting clip in the shader is great until you come to your shadow pass and your depth pass. And obviously, there's a big performance hit coming with that, so we need to, at a distance, we don't need to deal with that, but when we're close up, we need to be very careful, and we're still looking into the possibility of doing something where we can try to mitigate that cost and only pay the clip on the particular polys that really require it, which is generally a small fraction of the ship. So we definitely got more work to do there. So on some pictures, this is our Gladius ship again, as without any damage. We just add a bit of burn on there, that's just with the albedo change. Some normal changes for where we've been dented. Some more, it's quite hard to see on this, maybe it's easy to see on your screen. The normal changes from the burn, it's like a crinkled type of effect. If we zoom in a bit close, we can see that more. We can expose some bare metal underneath it. Cut some holes, and you'll see them holes look quite 2D. They look quite obviously just clipped out. And then we add in the screen space height map, and I'll just go back and forward on that. Again, it's quite subtle from a distance, but when you're close in, it really makes a difference, making it look like an actually 3D type of indentation there. A few other close-ups, and I'll show a video of it all. So you can see on the center of the wing here, actually, I'll just get the lowest point out. So, is that showing up? No, well, above that. So you can see type of the normal map changes. They're quite subtle, but we go to these type of great lengths because in our game, like I said, because it's first person, you can get up and explore and really investigate your ship and see what damage it's taken. So all these subtle normal changes are quite useful. That's more significant damage on the ship. It's obviously exposing some of the internals of it. The engine part there you can see is where we use the POM to model all them pipes and cables in there. Get a close-up of that bit there. And you can see what I mean, where we never really see the silhouette of it, so you don't see the worst problems of it. And I'll just do a quick video and talk over it to show you it in action. Is that playing? Well, that hasn't really worked for that. So we've got a few different types of damage here. This is just shooting with a projectile weapon, obviously. We're just cutting holes into it. Same thing again. You might be able to see when I cut through the wing, you can actually see holes straight through the wing. And I'll show some different weapons. So it's like a laser weapon. It does something different, doesn't cut through, but it burns and it removes the type of the paintwork and exposes the metalwork underneath it. to another weapon again, similar effect. And this is where things get interesting. This is us trying to blow parts of the ship off now. This is all just one mesh now. So like I said, in our old system, this would have been many different meshes, but this is all just the one single mesh, but obviously cut up into sections. Yeah. And then this is me just being silly. It was actually a specific request from our boss that I proved that we could write our name in the ship to prove the tech actually worked, so this is me writing Ali into it. And just got a few close-ups of. Yeah, so that's worked really well for us. So that ship has dropped from about 100 megs down to 15 megs by not having to, for the geometry data, for not having to store all these different damage dates we previously modeled. And the performance of it is quite a lot better. There is, we do pay a lot of ALU cost for LEM effects and a bit of memory for the damage map, but they're quite, we can cope with them much easier than we can with the geometry problems, and they're consistent, like I said before. We don't have to worry about these paging issues anymore. All throughout that example there was no paging going on, no memory was being moved around. So that's what is released at the moment. Well, actually, that was going to be released next week, but we've got a bunch of other stuff working on, which may be of interest. So one of them is working on morphing the geometry. To do that, we can't just, we didn't want to run a full simulation, like a soft body simulation on the ships. It was too expensive. There is support for that in CryEngine, but it's particularly heavy. So instead, as a simplified solution, we'd have to almost copy and paste the ship, and then we get the artist to like indent it, and it shows the areas which could be dented inwards, so they almost like shrink the ship. And then we get the difference between that and the original hull, and export that into the vertex data as like a blend shape or morph. We store it in 32-bit RGBE format. It's pretty good accuracy, but arbitrary range, which we needed. And then, then we, similar to the other techniques, when we just read this damage map, and if we find that it's dented, we just push them vertices inwards. Potentially here, we could use tessellation, obviously, because we don't really know the density of the polys versus the texture, so we can use tessellation to add more detail to show the dents in full detail. One of the things we're particularly interested in, which we're working on at the moment, which we made some good progress with, is GPU particles. Now, this is probably a perfect example of where GPU particles are really useful, because now we've got the entire damage system on the GPU. We know the position, the orientation, the color, the temperature, everything about the actual damage that's occurring. So by spawning the particles on the GPU directly, we have full access to all of that. So we can make it sync up much more closely with the actual visuals of what's happening in the damage. One of the issues we needed to manage, though, is a lot of the times you get like a GPU particle demo, they tend to be like fixed number of particles, like here's my demo of 10,000 particles, and every time they kill one, they'll spawn a new one, or they'll spawn a new one soon after. We had to deal with an arbitrary number of particles. Like obviously most of the game, there'll be 0 particles, but as we get into heavy combat, there could be potentially hundreds of thousands. So the way we decided to handle this, just mention some implementations. I've mentioned there, you can use like an append and consume buffer for like a free list, was the first approach we looked at, but our approach we tried to take a simpler approach, which is just to make the number of particles we spawn from each impact quite deterministic. So it's based on the surface area that we shoot. So if we shoot something, explosion of a radius 1 meter, we know within that we know there's a maximum number of particles we expect to emit. And we use that and then to treat the particle array as a ring buffer effectively. So rather than having a large buffer that is always updated, we can update just segments of that, or the segment we know which is of interest. I assume most people used ring buffer before, but it's just a simple 1D array where you wrap it around. So once you go off the end, you just start at the beginning again, and you just keep track of the start point and the end point. and then we just only call the compute shader to update the particles between them 2 points. Now, this does rely on us having particles that have a similar lifetime. If you can't use it if you have a big variation in lifetime, but for our particular case, it works well. And yeah, so if we do need particles with different lifetime, our strategy is going to be, which we haven't done this bit yet, we will just make a separate ring buffer for particles that need to live longer. So your smoke and fire might need different ring buffers if they need to be. This lets us have like a very large particle buffer, but we can just call the dispatch call on the subset we need, and it avoids us having to skip over too many particles that are basically like dead or unused in that buffer. So a few other extensions on this. Yeah, the tiled memory, tiled resources, something we really want to make use of. Unfortunately, our current min spec is 11.1 DX, so we can't really require it yet until our user base moves forwards, but they've been particularly useful here. We have an uncompressed damage texture, which tends to only be like partially filled, so ideally it would only be partially resonant as well, which is exactly what tiled memory would have given us, or tiled resources. So we definitely plan to come back to that to make some big savings in the future. And again, DX12 sounds like it would help us a lot there. So yeah, just a few other points to talk about. So scale issues. I mentioned before, our scale of the game is pretty enormous. The design is pretty grand, and you can see there the size of a 747, I think it is. I can't see what ship it is, plane is, but our ships are pretty big compared to a normal type of plane in the current day. And the ship at the top there is about 300 meters long. That's actually our smallest capital ship. The biggest ones are about 5-6 times bigger than that. Now, lots of games have had big ships before. It's no particularly hard thing just to scale up a model, but the horrible thing about our game, or the exciting thing, which way you look at it, is that these ships are fully modeled inside. So every single section of these ships is, you can walk around. So that big ship at the top has an engineering bay and has a bridge, has, the quarters and the toilets and absolutely everything on it. So it's bigger than many levels on many games just within that ship, and that's flying around doing its thing with 20 other ships shooting it. So it's pretty monstrous scale to deal with here. But we have the other extreme as well. Because it's a first-person game, we still have all, somebody stand against a wall with the wall right in front of their face. We have a UI which is actually projected onto your visor and on your helmet, which sits about 3 centimeters in front of your screen. It's not faked, so we don't do like, just slap it onto the screen afterwards. If you're a second player looking at yourself, then you can see the HUD actually sitting on somebody's visor. So yeah, we end up with needing to set the near clip to 1 centimeter and the far clip to 1,000,000 miles or something like this. So we had to make a few changes to CryEngine there. CryEngine only supports the 24-bit def buffer, so we had to move to the standard type of inverted 32-bit Z buffer, which didn't really come with any performance hit, which is good. We also had to upgrade CryEngine to 64-bit transforms, which was it's a monstrous task to move a big engine forwards like that. But luckily, the renderer can stay 32-bit. We've just managed to keep it all camera relative, and therefore, you never really need to have to deal with the 64-bit transforms. As a little brief diagram just to show the axis of 32-bit inverted float, but I guess most people are using that these days anyway. So I just wanted to, at the end, just to have a quick talk about our environments as well. So our environments, the way we're building them, because it's an MMO, we have tons of environments, and we need to build them very quickly. But they still have to meet the type of quality benchmark that our ships and our other assets have. So we opted for quite a modular approach where we just build small sections of levels, and then we just snap them all together. The designers can build a level really quickly like this. It also makes our art pipeline a lot easier by being able to outsource individual chunks of these kits. So artists and designers love it. Again, graphics programmers, maybe not so much. So here's just some of the kits there. So this is type of grey box art. This is nowhere near finished. This I just asked art to put something together. This is part of our single-player game. So you see all these different bits. We plonk them all together, and then here's another example they knocked up for me quickly to show type of how you can build this out of lots of different pieces. Also do the same thing for our space station. So here's another grey box piece of art for a space station, just type of showing the scale. So like I say, imagine that ship that was about 30 meters long that we could easily stand up inside the cockpit area. And you imagine the scale of that ship. I think it's space station. I think it's several kilometers long. So you can imagine the number of draw calls that go into that when you're building that out of small chunks. It's not really practical for the performance. Now, a typical game I've worked on previously would just combine all these meshes together and type of hand optimize it, but because of the MMO nature of our game, we can't really put in that much man-hour to an individual asset. It needs to be more automated. So we looked at a few things we could do to try and improve this. So so we go over what I've just said. So high poly counts. High poly counts tend to result in more use of tiling textures, and we don't use baking so much. I think that's like a general trend for the industry now, where when you zoom into a baked texture, you're always going to hit the limit of the resolution. You have to start using detail maps and tile textures more. But that also results in many draw calls for one particular mesh. I've already said we use lots of meshes to build a room and even more for a space station. So it's a bit of an explosion of draw calls. So one individual piece of our kit might be anywhere from 5 to 10 draw calls, and then a room could be several hundred of them. So you end up in the thousands very quickly. Obviously another point where DX12 could help, but I think we're so many draw calls that we still need to tackle this problem here and now. So we take two solutions for this to try and solve this. One is we looked at texture arrays, but the type of, with DX11, the fact they have to all be the same resolution doesn't really help us for our streaming engine. Like I said before, we rely really heavily on our streaming, so we can't just have an entire level's textures permanently resident just for the sake of having them in a texture array. So that didn't work out practical for us. What we did find out is that our textile density is so high that we actually don't really need to use the full resolution texture. So if we have a texture array of something like 256 resolution, we can actually fit the whole level's textures in about 15 megs, which is much more manageable. And obviously 256 resolution is going to look terrible when you're up close, but we just only use it for the LODs. So once you're about 20 meters away, we can drop to this. It means our LODs all go in a single draw call, but we still maintain all of the streaming engine and the detail up close, but it's a nice, quick, easy win for us to suddenly drop like a 10 draw call mesh down to 1 draw call. And if we make any LODs equally, it'll bring all them down to 1 draw call as well. And probably straightforward, but simple point to mention is we keep the vertex buffers ordered by which textures, with the verts by which texture we use, so we still can opt to use the high-res textures on the LODs. So you can type of choose an arbitrary distance where you want to swap to be your low polys and your low textures. They don't have to be linked in any way. So that gets us somewhere better, like say it brings your 5 or 10 draw calls down to 1, but we're still quite a lot over for what we can cope with on DX11. So we use a solution similar to what Killzone published a year or 2 ago, which is just to merge all our meshes in a type of procedural manner. So each artist will then go take their one modular piece of kit, and they'll make quite an aggressive LOD chain for that and drop the polys, say like 75% at a time. And then we just do some type of heuristic algorithm where we just try and find pairs of meshes that would reduce the draw calls as much as possible with the lowest memory hit. And then we iteratively run that over the entire scene and give it a fixed budget it can use, say like 50 megs or 20 megs, whatever it might be, and then just let it do its work. And that saves us quite a lot of draw calls. That bit's not been released to the public yet, but it's looking very optimistic that. It does rely on the artists being quite aggressive for their LODs, though. Combining meshes, obviously, you're paying quite a hefty cost there in the combination process. It's not quite as perfect as if an artist had hand done it, but it's automatic and it takes seconds rather than hours, so it's a bit of a no-brainer. We'll still have the ability for the artist to go in and hand do a lot if they feel like the automated system isn't quite good enough. So, and that's my last slide. There's a hell of a lot working on this game. There's a ton of features that we're trying to cram in the next year. So that's just a subset of what we're doing. There's lots more stuff we'll probably be talking about in the future, particularly gas clouds is one thing we wanted to talk about today, but didn't quite get it to a level where it'd be good enough to show. We've got all these other fun things in space as well, asteroid fields and such. Yep, and thanks for listening. Only thing I want to mention while we're here is that we're hiring. Seems impossible to find senior graphics programmers these days, but yeah, Manchester, UK, Frankfurt, and Santa Monica. We have offices all over the place. Definitely looking for talented people. So I think I'll leave it there and open up for questions.
Hi. Hi. You started your talk saying you had extremely high polygon counts. Do you have a range per frame you're talking about?
We have, it depends if you want a range of what I think is sensible or what we have, what I'd like. So our ships will be anywhere between, once you're up close, a small ship might be about 500,000 polys. The larger ones are in the many millions, but they're so large that you would never see the entire ship at once. If you were close enough to the front of it, you wouldn't be able to see the back of it. But the total assets for a capital ship is in many millions, like 5–10 million at least. The characters are, say, in the hundreds of thousands, easily over 100,000. And a total scene, we're probably looking at, it varies a lot. We haven't settled on a final budget for it, but it's many millions, much more than I worked on previous 360 games, for example.
So
an order of magnitude higher.
Per frame, are you above 10 million or below 10?
It varies a lot, to be honest. One of the things we've really found a struggle with is, because the MMO nature of our game, we don't really know the worst case scenario, and we haven't got to the point in the development process to find that worst case scenario. So we might be in a hangar, and it might be like 2 or 3 million polys, but then you put 20 ships in it, and then suddenly it becomes 30 million polys, and then we have to optimize, and yeah, we don't really know our worst case yet. Our worst case is going to be once we've got a few of these capital ships flying around together, crashing into each other with a whole bunch of fighters around, and we haven't quite got there yet. It'll be as high as the hardware can cope for the time, though. Chris Roberts has made it completely clear we'll absolutely push the latest piece of hardware as hard as we physically can. He doesn't want this to be a low-end game. It's got to be the best it can be.
Thank you.
Nice. Cheers.
You mentioned wanting to do the geometry morphing, and I guess I wonder how would you deal with that once you create holes? You're basically changing the topology of the mesh, right? So you cut a hole into the wing, and there used to be a vertex there. What is it morphing toward? Does that still work, or it seems like you have to start connecting different triangles?
I might not understand the question. I don't see there's not a particular problem there. The cutting holes is just clipping out the geometry. We still morph it in the same way, but then we just discard some of the pixels.
It becomes invisible.
Yeah. So.
Okay.
It seems okay, but like I said, we have not got that on the public demo yet, so we get to test the performance of accurately test Howell tessellation and this. Obviously, we feed in this extra vertex data for the morphing, and we have to read the damage map in the vertex shader. There's quite a lot of overhead on this, so we need to run performance tests to see how practical it is and work out, how high spec PC you need to make that actually realistic.
Thanks.
Cool.
Great talk. Question for you about the decal tiling optimization.
Yep.
Could you go into a little more detail about how you actually do the sphere fitting, building the 4 bounding spheres for the?
Oh yeah, it's pretty simple though. We don't have anything particularly complicated there. We just bounding box and then assume the middle of the bounding box. It would be ideally be an AABB, but we just use a sphere for more optimization. So we just use the center of the box and just take the sides of it and turn it into a sphere like that.
So it's just the 4 chunks, just uniform? Okay.
Yeah. It's nothing particularly fancy. It still gives us a decent speed, but we need the code that does these bounding sphere checks that uses the data to be as quick as possible. So it doesn't really matter too much about how accurate that bounding sphere is, as long as most of this texture is we're trying to discard work that is clearly miles away from the actual impact point. So it doesn't really matter. It's just a rough distance check, really.
Okay. Cool.
Anyone else? We all wrapped up. Oh.
How do you manage Z buffer with long-range issues?
Using the distance thing. Well, I mean, beyond, we just use the inverted 32-bit F depth buffer format. That seems to all we need to do, and that seems to handle everything we've thrown at it so far. So we have our far clip. The 32F, you get the precision is proportional to the distance. So as long as you, if you have something that's 1 meter away and you put something a millimeter in front of it, that'll work. But if you're talking planetary scale, as long as you don't put something equally a millimeter in front of it, then you won't get Z firing. It's proportional to the distance. So as long as when somebody's making a very big asset, they equally make the separation between polys proportional to the scale of the object, it tends to all be fine. It ends up pretty crazy, the accuracy on 32F once you've inverted it, so I don't think anyone's realistically going to be able to make that Z fight. It'd be pretty dodgy artwork, I think, if they managed to.
Thank you.
Is that everyone? Cool. Thanks a lot, guys.